So now we're ready to talk about modular arithmetic, which is one of my favorite topics that we're going to talk about all semester. It's one of, I think, kind of the unifying topics for many of the different things that we've been talking about over the course of the semester. It's going to be a good playground for proofs. It's going to kind of tie together some of the stuff that we did with even and odds. There's going to be some related results that'll involve induction. And it's just a really nice idea, really nice area. This notation that we're going to use is due to Gauss. I think part of the niceness of what we're going to talk about is actually the notation. And so notation is something that often gets taken for granted. But this notation basically tells us everything that we need to know about modular arithmetic. So we'll go from there. So modular arithmetic. Given any two integers, a and b, and given an integer m, where m is greater than or equal to 2, we define that a is congruent to b mod m if m divides a minus b. Okay, so this is the basic definition that we're going to need in this chapter, and really it relies on the basic definition that we had for division, so that m divides a minus b. So this is important enough. I want to redraw that division sign here. Okay, m divides a minus b. This is modular arithmetic. So we say that a is congruent to b mod m if m divides a minus b. I want to emphasize this three equalities here is the notation that I was talking about that makes it nice. We'll explain very soon what that is exactly, but I just want to emphasize that this is a description of a relationship between two integers. This is different than the mod m that we had before. Here, when we had mod m, so this is a simple point, but I think it is important. If I were to write -7 mod 4, and that's a capital mod, equals 1. This equals 1 because this is some integer. It's the remainder when you divide by 4. Okay, this is a slightly different idea down here. If I say that a is congruent to b mod m, that means that they have some relationship, and this is the relationship. M divides their difference. Okay, so for example, I think this is important enough. For example, if I were to take 12, that would be congruent to 2 mod 5, and that follows because 5 divides 12 minus 2, right? 12 minus 2 is 10. 5 divides 10, so 12 is congruent to 2 mod 5. If I were to have 14, that's not congruent to 1 mod, say, 5, since 5 does not divide 13, right, being 14 minus 1. So 14 is not congruent to 1 mod 5. 12 is congruent to 2 mod 5. Okay, so this is a good example here. So one way that I like to think about this, just to make this slightly more intuitive, is I think of working mod 5 as kind of working along a circle. Okay, so I'm going to work along a circle, and basically we're going to start at 0, and I'm going to put 5 numbers here. So this is kind of like a clock with 5 hours on it. 0, 1, 2, 3, and 4. And addition refers to, so if I think about 12 being congruent to 2 mod 5, what that means is that if I were to start at 0 and count to 12, we will go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we would end up at 2. So 12 is congruent to 2 mod 5. Okay, so we can kind of think of working mod 5 as kind of working along this clock. Sometimes this is called clock arithmetic. Just to emphasize that this is called clock arithmetic, 1700 hours is 5 p.m. mod 12. Okay, so that's another example of a relationship of two integers being congruent mod m. I want to point out, why do we insist m is greater than or equal to 1? Well, we want m to be positive just so that things don't get silly. But also, we don't want m to be 1, because then everything would be congruent. We know that 1 divides everything for all x. That's one of the propositions that we proved. 1 divides every integer. So everything would be congruent mod 1. Mod 1 isn't really saying anything. Okay, so that is what it is there. Now, I want to give another definition, or rather, whether you want to call it a definition or another way to think about modular arithmetic. It turns out that there's a few different equivalent ways to think about modular arithmetic. They're really all the same way, and we'll explain as we go along. But it turns out that A is congruent to B mod M if and only if M divides A minus B, which is to say that happens if and only if there exists an integer k, so that A minus B is equal to mk, or if and only if, so this is equivalent to saying that there exists an integer k, so that A is equal to B plus mk. Okay, which is, I'm really just rearranging and kind of unpacking the definition, but this is actually going to be incredibly useful for us. Two integers are going to be congruent mod m if and only if they differ by a multiple of m. So 12, this is an easy way to see that 12 is congruent to 2 mod 5, because their difference, 12 minus 2, is a multiple of 5. That's basically what we said above, but I think this formulation is particularly nice. One other fact that we're going to use is that A is congruent to B mod M if and only if, when you take A and you divide by M, the remainder that you get is the same as the remainder when you divide B by M. So for example, if we were to take 12 and divide by 5, we will get 2 with remainder 2. And if we were to take 2 and divide by 5, we will get 0 with remainder 2. This remainder 2 bit is what makes these congruent. We have the same remainder. So that's, again, another way to think about what it means for them to be congruent mod M. Okay.